So we've now are well on our way to coming towards what we had accomplished with a simple harmonic oscillator. We've discovered what the key operators are onto which to build our algebra for finding the states of this system very efficiently and very effectively. You might recall for the harmonic oscillator, there's one more real connection we have to make back to H, which is not only understanding these commutating relations, but we have to actually write H. So we're going to have a goal then is to express H in terms of these operators. Now this is going to be a much more complicated type of an operation than we had before, because after all, the Hamiltonian has this very complicated p squared involved in it, right? This complicated Laplacian operator, and our angular momentum operators themselves are not trivial types of operators here. We have all of this cross product business going on. So whenever we are faced, this is just general advice for you all, whenever you are faced with a very complicated problem, one of the first most powerful things to do is to solve a simplified version of that problem, maybe even in a context where you are much more comfortable, and then go ahead and look at the full-fledged problem. So in this case, what we're going to begin with, we're going to begin classically. Let's ask the classical question. What is the relationship between angular momentum and energy and the Hamiltonian? Well, if you think back really to your first, physics classes, right? Maybe even like the high school AP physics class, you might remember something like this. There's a relation that tells you when I have a rotating object, the kinetic energy, right, which is a good portion of the energy, has something, an expression like this. It's something like 1/2 times the moment of inertia times the square, right, of the angular rotational frequency. Now, this doesn't directly relate us to angular momentum, but also remember you had this relation that the angular momentum is the moment of inertia times the angular velocity. So then if I solve for the angular velocity omega as L over I and insert that in here for omega, what I end up with is kind of a cute expression, right? I'll get L squared on top. I'll have I squared on the bottom, but there's an I on top, so there's one net I on the bottom, and of course there's a 2 on the bottom, so it's L squared over 2I. So it's a lot like how we normally write our kinetic energy when we're dealing with Hamiltonians. We've been trained to actually write it as momentum squared divided by twice the inertia, or in this case just twice the mass. So there should be a pretty close relationship. Now this, of course, is just for, if I have some object rotating around some kind of a pivot, right? This is not a general idea of a general moving particle, but at least it gets us into, the right sort of frame of mind for what we're looking for. If I want to be a little more precise about this, we can go another step further. The angular momentum, the moment of inertia for just a simple point particle, which is what our electron in our atom is, you might remember that moment of inertia is m times the radius squared. So classically speaking, there should be a relation very much like this. The other neat thing is, and we can kind of see where this is going to be going, the two m's cancel. So if I ever want p squared, which is my root to getting to my kinetic energy, I'm expecting that to be something like 1 over r squared times the angular momentum. The other way to think about this is to say the angular momentum squared gives me r squared times p squared, and that does seem about right? That looks like L equals rp, but we have to be very careful. Remember, there's some cross products involved here, right? This would really be the lever arm times p. Frequently that's written as something like r perpendicular times p, or the other way that's often written is as the radius times the perpendicular momentum. So a better way of thinking about this is that the angular momentum squared actually tells me information about the square of the perpendicular momentum. It gives me information about the kinetic energy perpendicular to the radius, basically the rotational kinetic energy, which after all is the expression that we began here with. Okay, so that's sort of a phase one on the classical analysis. If we want to be more rigorous about this, we really should go back to the true definition of what L squared is and see if we can prove something along these lines here.